All right, so welcome back. I'm recording the answers to the fluids and waves review. So I skipped over all the terms and definitions and such because I figured you guys can find those either on the internet or in the lessons throughout those or activities. So I'm just going to go through the things that I think are maybe a little more open-ended. So the first part, you were asked to sketch and describe a label parts of a transverse wave and a longitudinal wave. So I did my best to draw it on the mouse tracking pad, but that didn't work very well. So later on, I think we have better pictures maybe. But because I think this question gets repeated for the transverse wave. So the transverse wave is the one that kind of looks like what you would typically think of when you think of a wave. And you have your crest, which is the highest point, the trough is the lowest point. Your amplitude, which is your highest distance away or lowest distance away from the equilibrium, which is that central position. I labeled A for amplitude. And then just describing the transverse wave, the vibration is up and down in this one, and the wave moves to the right, so they're perpendicular to each other. For the longitudinal wave, I couldn't really draw this very well with the mouse pad. I tried to draw the slinky, but it didn't work. So we have our compression where the coils are kind of tightly packed together over here again. And then the rarefaction is where the coils get stretched out. So that would be your rarefaction. Vibrations are parallel to the wave motion. So the vibration is hands moving back and forth, the disturbance moving, I guess, like left to right across the page, and the wave travels left to right across the page as well. So there's your first kind of drawing the waves. Then we got into a problem with volume and mass and density and such, so and buoyant force. So it says a rock has a volume of 0.005 meters cubed and a mass of 7 kilograms. Find its density. So this part is pretty straightforward in the beginning. They give you the mass and the volume. The density of rock is what you're trying to find. So that's just the mass of the rock divided by the volume of the rock. So 7 divided by 0.005 gets you 1,400 kilograms per meter cubed. So just straight division. Next, it asks for if the rock is submerged, so being submerged, you mean the volume is totally in the water or the fluid, that has a density of 800 kilograms per meter cubed, what would the buoyant force that it experience be? So the only new piece of information they give you is 800 kilograms per meter cubed, which is the density of the fluid. To find the buoyant force, you got to use the buoyant force equation, which is the density of the fluid that it's in, the volume that's submerged times g for the acceleration due to gravity. So it's going to be 800 times that 0.005 times 9.8. So when you do that, you get 39.2 newtons, and that's the buoyant force. The third part of this question asks if you had a second rock which has made of a different material, it's the same amount of mass, so it's still 7 kilograms, but the volume increased. How would the buoyant force act on this? So if the new rock has a larger volume, that means that your volume submerged is getting bigger. So this 0.005 is becoming a bigger number. So the buoyant force is also going to increase, because if you multiply it by a bigger number, then the output, the buoyant force, is going to also be bigger. So that's that problem. After that, we got into some refraction problems. So just to be clear, this is our boundary going horizontally. That's the way that I intended it. And then the normal is perpendicular to this. So the normal is the vertical line that we're going to measure all our angles from. So just to be clear, to make sure everybody can see that. So similar to what you did in that lab activity. So the first ray, the first example, has an angle of 15 degrees and the index of refraction is 2.4. And then it's going to go into an index, different material that has an index of 1.6. So that's less. So if you have less dense or less, a smaller index of refraction means it's less dense, which means the light will go faster through it. And when it goes faster, it bends away. So that's how I knew this is going to bend away in this case. So still sticking with this one over here on the left, we can go ahead. Well, I guess I'll talk about the one right because they're going to show at the same time. So the one on the right over here, different scenario, different indexes. Instead of going from a more dense to a less dense, it's going from less to more. So it's going to slow down as it enters the second medium, and that's going to make it bend towards the normal. So I really just do the same equation twice with different numbers, and you can see the different answers here. But I just use Snell's law for the first part. What happened to the third piece? Okay, so something disappeared, but maybe I can come up with it in a second. So anyway, coming back to this first example, I used Snell's law, the first statement right here, and then I just plugged in the values. So I started at 2.4 sine of 15 equals 1.6 sine of theta 2. Make sure your calculator's in degree mode if you're doing this, so you'll get the right answer. So I just did the math and solved for theta 2, and if you just track this out, you should get 22.84. I think the part that I had before where I calculated the speed in the medium, I'll get back to that here in a second. So for the next one over here, same kind of setup, starts out this time in 1.5 with sine of 25, and then it equals 1.75, which is what it's going into sine of theta 2. You're looking for this new angle. So when you do that, you get 21.24. And both those answers agree with what we expected to happen. So if it's going from a more dense to a less dense, it should speed up and bend away. So that's 22.84 is bigger than 15. And in the second example, it's going from a less dense to a more dense, so it should slow down. So it bends toward, and that's 21.24 degrees. The analogy that I use sometimes in class for this is like, if you're going faster, if you're say playing, you're getting chased by somebody, right? And if you go faster, you're going to get away. So that's the first case here. So if you go faster, you get away, it bends away. And if you're getting chased by somebody and you go slower, then you're going to get caught and you're going to move towards them. So that's moving towards here. So hopefully that helps like clarify, or like a simple rule to help calculate it. The last part of these problems, if I come back up, it says calculate the speed of light in the refracted medium. So the refracted medium is what it's going into. So you're just using n equals c over v, and you're going to solve for v. So it's really c divided by n. So 3 times 10 to the 8th, that's the speed of light. In a vacuum, you're going to divide it by the 1.75 over here, and you get 1.71 times 10 to the 8th. For this over, I don't know if I can copy it. Hold on. Sorry. There we go. Oh, no. Okay, well, went all the way back there. Let me grab it. No. Okay, a little bit of technical difficulties. There we go. Okay, let's try to put it over here somewhere. There we go. So this changes from, there it is. I don't know. That's the right work. I don't know what happened to it. It just appeared and now reappeared. Maybe it got put on the wrong page. But 1.6 times equals 3 times 10 to the 8th divided by v. We're solving for v, so this is the answer for this one over here. That's really strange. I'm not sure what happened. So anyway, here's the better picture of the transverse wave with a nice smooth curve instead of me trying to draw it. I think on the review online, I don't know why, but it might have gotten kind of distorted with some weird lines on it. So hopefully you can make this out and it makes sense to you. But you got your crest and trough and amplitude and wavelength again. So nothing too different. I think it did ask you to do a couple problems after it. So you had to calculate the speed, I'm sorry, the period and the speed based on given the frequency and the wavelength. So you're given everything you need. To find the period, it's just the inverse of the frequency. So it's 1 divided by f. So it'd be 1 divided by 600, which is that number. And then for the velocity or speed of the wave, it's the frequency times the wavelength. So just 600 times 0.6. It gives you 360 meters per second. So that's that one. So I think the last one that we have on this video is this pressure due to depth idea. So it says a rainwater collector is open to the air, contains a column of rain with a density of 1,100 kilograms per meter cubed. If the liquid is 3 meters tall, calculate the total pressure at the bottom of the rain collector. So the total pressure would be the atmospheric pressure plus the pressure due to the fluid. So you have, it's open to the air, so you have atmospheric pressure or air pressure and that fluid pressure from the water. So the air pressure is a constant. Again, we're just going to use 1.013 times 10 to the 5th. And then you're going to use this pressure in a fluid equation. So the density of fluid times the gravity times the height or depth of that fluid. So when we plug all that in, you should get 133,640 pascals. And then you're going to use that answer for part B, where it asks you to calculate the area of an object, at the bottom of the pool if it experiences 40,000 newtons of force. So it's this pressure, and pressure again is just force over area. So you're going to solve for area, so force divided by pressure. And when you do that, you get 2.93 meters squared is the area of that object. So I think that's the review for that section. Yep. So hopefully that was helpful, and I will talk to you guys later.